Audio check. Good.
It's totally a war.
Why are there advertisements on my Twitch channel? Somebody is making money and it's not me. All right. Oh, good. We did a bunch of these. Somewhere around here is the cord for this thing. There it is. And the other side of it. All right. Pretty. So we did linear and cubic. We did cubic interpolation, but did we do Verdin and Ferris? Did we do cubic splines? We did not. Splines are important, y'all. Splines are pretty important. It's probably what I should do next and hold off on quadratures. Tri-diagonal matrix, my favorite kind. Yep, I think that's what we should do next. Hello, we are looking at cubic splines. I'm just doing a little bit of reading to give myself a refresher on what's going on here, and I'm gonna try and give an explanation in a moment. Explanation of what is a cubic spline, what is it for, how can we use it in video games, and I think I'm ready to do that. So, natural, yeah. Okay, let's do it. I think I'm gonna need this, and we're gonna make a new. Did I never make? Here's bisection, fixed point, floating point, Newton, floating point operations. Oh, I only made one for linear. Wait, did I do cubic? I thought I did cubic. I did cubic. Okay. Why don't I have a folder for it then? What happened to my cubic? May have gotten deleted. Oops. Well. Come on. Copy. 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 Paste. I'm trying to do that. Paste. Here we go. Cubic splines. Let's go in there. Yeah, I'll bet I just deleted it accidentally. That's a shame. Yes. And this is root finding. Why is it root finding? Something weird definitely happened because I opened the linear interpolation files and I'm now looking at root finding. What else? All right. Cubic splines. Hey, Jan. Nice to see you. I'm doing great. So, cubic splines. Last time, let's see, we did cubic interpolation, which was you have a function that is flat, and then you want to get it to be that value, also flat. And so you make a cubic function that interpolates between the two such that it does it smoothly, like the derivative is 0 here and 0 here. And we derived how to do that, and that was cool. And just a cool note for all the wonderful people on the stream, I've actually used this to interpolate between things that are not splines at all. I'm sorry, things that are not flat and flat, but rather like if your object is moving, and then you want it to back up a little bit, and then move some, and then go back to where it was moving before, you can repeat the same process we did as last time. But instead of using 0 for the derivative right here, you use whatever the slope of this guy is. And you use, whatever the slope of this guy is here. So the equations are more difficult that way because you have you can't, like, if you remember, we had a bunch of zeros in our matrix, in our system of equations that we're not going to have anymore. And that makes it a little bit more difficult to solve. But it can be done. And what we're going to do this time is basically that, which is why I bring it up. So let's say I have 3 points. And I want to, okay, I'm flat before it, and I'm flat after it. And I want to make a nice cubic spline here, and another nice cubic spline there. So this will work if I just assume that the derivative here is 0. And then, let's say I have this many points. And I do it again. This is what I'm going to get. Because again, I'm assuming that the derivative at each point is going to be 0 when I make my spline. Which is maybe not what we want, because, so we start low, and then we get this high point, and then a little bit less of a high point, and then a low point. But probably we want something that looks more like this, right? We don't want it like this, not quite as high point as just a transition going way down to the low point. And we don't want to completely stop there and go to zero derivative as we're going through that point. So we want to have like we want to have a smooth transition as we're going through this point, but we don't want the curve to completely stop dead. So cubic splines will help us with that. And these are all the rules for a cubic spline. I'll go through them one at a time. We have a bunch of points here. This is, let's see, this is x. X naught to xn. So this is x naught. This is x1. This is x2. This is x3. This is x4, and n equals 4. So we have 5 points in total. So for each one of the, so S is our cubic polynomial, and it represents one segment of this, so like this guy is S1. This guy is S2. Did you start with 1? It starts with 0. Yeah, it starts with 0. So S naught, S1. This guy is S2. This guy is S3. So at each point, at the endpoints of each one of these S's, the cubic interpolation function should be equal to the actual value of the point, right? So let's see. These x's are x values, and so here we have our y values, f of x. So this should be f of x naught. This is a point x1, f of x1. This is a point x2, f of x2. And so on. x4, f of x4. So these are the x coordinates down here. I'll mark them. Try and make them really clear. Try and make it really clear what we're doing, because this can get kind of crazy. So right here is going to be f of x3, and it just corresponds to the value at x3. Here we're going to have f of x0. Here we have f of x4. Here is f of x2 and f of x1. So it's just saying that for each s, for each polynomial at its endpoints, we want the polynomial, like we want the value of the polynomial at the value of this s naught polynomial at x naught should be equal to f at x naught. In other words, it should be this point. And the value of s naught at x1 should be equal to f of x1. It should be equal to this point. So we're not going to stray from the cubic, we're not going to stray from our original data points any. Let me back up here a little bit and explain why we're doing this, like why we want cubic polynomials. And a good example is, we're going to go back to Blue Ocean, which was my tech demo that I showed a while ago. The camera, yeah, I'm live on Twitch, cool. The camera is defined by a cubic spline. Like, I put a bunch of points in the world, and then I said, hey camera, I want you to to like follow along these points. So pausing that. Here's a point, here's a point, here's a point, here's a point. Like at time 0, I want the camera to be here. At time 1, I want it to be here. At time 2, I want it to be here. And at time 3, I want it to be here. Where like this entire sheet right here is my XY plane. Let's draw some axes on this thing. XY. So like this is gonna have some XY coordinate. And this is gonna have an XY coordinate. And so on. So at time equals 0, I want it to be at this coordinate. At time 1, I want it to be at that coordinate, and so on. Except if I just draw a line, like between these two, if I use linear interpolation, then everything will work fine until time 1, and then the camera will take an abrupt right turn when it starts heading to time 2. So linear interpolation is not a good solution for the camera problem, because we're going to have a very abrupt change when we start going to the second point that we're defining. But we don't want to like, we want an easy way to specify where this camera, like what the camera should do, where this camera should go. We don't want to have to, and if we can just specify the points that the camera should be at and what times they should be at, and then hopefully we can have the computer draw us a nice soft curve like this that goes around those points. That's a pretty classic example of something that you would use a cubic spline for. So that's what we're doing here. So this is a 2-dimensional cubic spline. I'm only doing a 1-dimensional cubic spline. You can pretend that these x's on the x-axis here are actually time. At time 0, I want my value to be f of x naught. And at time 1, I want it to be f of x1, and so on. Right. Good. And then, how I said before, if you look at the orange line, our camera would be stopping. If it's following the orange line, it would be stopping completely when it hits x2 and continuing on. And the way that looks in the 2D picture is, we start stopped, of course, but then we are going to time equals 1, and then we stop at this point before we keep going. We don't want to stop. We want to keep going smoothly through the point at a constant speed, at a more or less constant speed. So a cubic spline is a way to build a smooth path out of a set of points in the world. I think that's I like that. I'm going to write it down. Cubic spline is, you take a set of points and it becomes a smooth path. I'm writing that down so I can remember it later. It's a way to make a smooth path out of a set of points. Good. So where were we? We're going to use these cubic polynomials to specify our path, but we don't want things stopping abruptly at each endpoint of our piecewise polynomial. I should probably define the word piecewise. I don't think I've talked about anything like that, and it's just what it sounds like, really. This is a piece, and then this is a piece in here, and then this is a piece in here, and then this is a piece. So this entire function s is not a polynomial, like s, the entire green function here, but it is a piecewise polynomial, which means you can break it into a finite number of pieces, each of which is a cubic polynomial. All right, so we want the endpoints of each piece to be equal to the data points that we've given. So that's probably the most obvious constraint that we have on our cubics. So let's look. Yep, wait, what's this? This is the left endpoint and the right endpoint of each one. Okay, good. And the left and the right. Oh, yeah, this is implied by B. Yeah. So we can even skip C because it just says what already was said by B. It just says that the right endpoint for one of them should be equal to the left endpoint for the other, right? The right endpoint of this one should be equal to the left endpoint of that one. So that's if they're both equal to F, then that's implied. All right. So now the first derivative of the left one of the let's see. That is the left endpoint of the right one should be equal to the first derivative of the left endpoint of the right endpoint of the left one. So let's see. If I have S naught that meets S1 right here at x1, then the first derivatives of both curves should match at x1. So how does that look? The derivative of S naught at x1 should equal the derivative of S1 at x1. That's this point right here. So we're not saying that they both should be equal to 0, that both slopes should be equal to 0. We're just saying that both slopes should match each other. So that the particle doesn't have to come to a complete stop. Particle, I say particle, but it could be anything. It could be a camera, it could be any, it could be a path that your character is taking through the world or whatever. So. And then the second derivative, so same thing but for the second derivatives. The second derivative of this piece as it's approaching x1 should be the same as the first derivative of the second derivative of the next piece. And why do we have that one? So let me try and give. Well, no, I've talked about this before, haven't I? I had a video about acceleration and derivatives. So the second derivative is the same as the acceleration of the function, right? So this is just saying that the acceleration of the right endpoint of S naught is equal to the acceleration of the left endpoint of x1. And this is again to retain like the smoothness of our curve. This is a level of smoothness that is probably not visible to the naked eye. But in fact, if we don't have enough constraints on this function, then so this is the problem. We have C3x cubed plus C2x squared plus C1x plus C naught. So this is going to be S naught, right? It's going to be the equation for the function between these 2 points. So S naught of x. So if we have no constraints on this function, it can be any function, and all of these c's can be whatever you want them to be. They can be magical. Any real number anyway. So if we put one constraint here, and if we say that S naught of 0 should be 0, then that means we're going to lock down one of these coefficients. We're going to see that C3x is the same thing we were doing before, x squared plus C1x plus C naught equals 0, but x is 0, so this is 0, and this is 0, and this is 0. So C naught equals 0, right? So let's put one, so when we, okay, and now our function we know is C3x cubed plus C2x squared plus C1x. So we set a constraint on the function, and we lost one parameter. So let's set another constraint on the function. Let's say the derivative at 0 should be 0. So then the derivative of S naught of x, yeah, is 3c3 plus 2c2 squared plus c2, oh my god, 3c3x squared plus 2c2x plus c1. That's the derivative. So then S naught prime at 0 is going to be, well, this is 0 and this is 0. So it's just c1, and we said that should be equal to 0. So we know c1 is 0 too. So we set another constraint, and then we lost another coefficient. So for a third degree polynomial, we need 4 constraints to resolve 4 coefficients. It's not always going to be as pretty as this, where like sometimes you give one constraint, but that doesn't knock away completely one of the coefficients. Sometimes you need to get all 4 before you can knock all 4 out. But in general, if you have a 4th degree polynomial, you do need 4 to knock all 4 of them out. So, how many constraints do we have here? There's a bunch. We have 4 for S naught, we have 4 for S1, 4 for S2, and 4 for S3. That's 4 times 4 is 16. 16 constraints. And each of these is a constraint. So let's see. We're constraining the left and right, and well, each of these is actually a bunch of constraints rolled up into one. We're constraining the left and right endpoints of each segment. So that's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 constraints in all of this. 8 constraints in there. And then we're going to do the same thing here. We need, wait, something's wrong. Yeah, something's wrong. No, nothing's wrong. So the right endpoint here should be equal to the left endpoint here. So that's another 1, 2, 3, 4, 5, 6 constraints. Here are 6 constraints. And that means this is another 6 constraints. Yeah, there's definitely something wrong, because this adds up to 8 plus 12 is 20. This adds up to 20 constraints. That's too many constraints, guys. Too many constraints. What did I do wrong? If you have more constraints than you have coefficients, then that's bad news, right? You can't, you're not going to be able to solve, you need exactly as many constraints. So let's see. One, 2. So 2 times n minus 1, and n minus 1 is 3? What? 0, 1, 2, 3, 4. I know, there's 2 times n. So this is 10 constraints? 1, 2, 3, 4, 5, 6, 7, 8. This is 8 constraints. So these two make 8 constraints. I think that's true. I think I'm good there. We have another bunch of constraints here. Oh, 1, 2, 3, 4, 5, 6. No, that's 6. That's right. And then another 6 for the second derivative. That's 12. And then they actually have a few more constraints. They have that the second derivatives at the endpoints, like the second derivative here is 0 and the second derivative there is 0. So that's two final constraints. So they have 22 constraints for this example. Okay, well, should I spend more time on this, try to figure out why the number of constraints are wrong, or should I just move on? Let's take one more stab at it, make sure we're doing the right thing. So this is a constraint, and this is a constraint. For 0 to n minus 1. So there are n of these. So it should be n, which is 4, times 2, which is 8. That's the correct number of constraints. And then this is one constraint for each n, and there are n minus 1 of them. So there are 3. So wait, this is only 3 constraints. 1, 2, 3. Yeah, and this is only 3 constraints. So alright. That's it. That's what it is. This is 3 constraints, this is 3 constraints. So I was counting it twice, which was wrong. So it's one constraint because the constraint is that the derivative of the right endpoint here should be the same as the derivative of the left endpoint there. That's one constraint, not 2 constraints. So 8, 9, 10, 11, 12, 13, 14, 15, 16. The 2 last constraints are that the second derivatives of both endpoints could be 0. So we can actually have any constraints we want. If we want to say, you know, we have our n plus 1 points, and we want to say that the first, you know, okay, this one is pretty obvious. We should probably always have these constraints. So that will get us 2 n constraints right there. But we have 4 n constraints that we need total. So that means we need to come up with 2n more constraints. So if I want to say that, well, the first derivative here is 0, and the second derivative here is 0, and the third derivative here is 0, and et cetera, et cetera, et cetera, so the 2nth derivative here is 0. And then, so I would write that, this is hypothetical. Hypothetical. Come out over here in hypothetical land. Hypothetical. Okay. So we're going to have S naught at x1 equals S1 at x1, and etc. So all of these will get us 2n constraints. And then I want to say S prime not equals 0. S double prime not equals 0. S, and so on until S 2n, S naught, so this 2nth derivative of S naught equals 0. That will be a really, really weird system of equations. Actually, will that even do me any good? No, I couldn't do that. I couldn't do that because at some point, remember this S naught is actually a cubic polynomial, and I can only put 4 constraints on it total. So this won't even work. But I could do first, second. So first derivative is 0, second derivative is 0. First derivative is 0, second derivative is 0. And then just do that, you know, n times. And that would get me another 2 n constraints. So, you know, I can make my constraints here whatever I want, is the message that I'm trying to say. And in the end, I'll still be able to solve for what the coefficients could be, as long as I have 2 n constraints, and, you know, no more than 4 constraints per piece of the polynomial, then I will be able to solve this system and get my nice, smooth camera motion. All right. So how does that look when we do this? How does that look? S naught of x equals 0. In other words, C4 x4 plus C3 x3 plus C2 x2 plus C1 equals 0. And then S naught of x, sorry, that should be f of x1, right? So this is my first constraint, or f of x naught. This is x naught. And then this is my second constraint. Little x naughts here. C4 x1 plus C3 x1 cubed plus C2 x1 squared plus c. Oh, what am I doing? These are cubics. Plus c naught. Oh man, I drew all my numbers wrong. Erase, erase, erase. Okay, so here's naught, here are ones, here are twos, here are threes, 3, 3, 2, 2, 1, 1. And this should be f of x1. Okay? And then I have, you know, and then I have 2 more constraints for s naught. So let me go on to s1. S1 has some constraints on x naught. Actually, it'll probably have constraints on s1. And then it'll look the same way. It'll be C3 x naught cubed plus C2. I am getting to a point here, etc. equals f of x1. So I have 4 constraints here, and I have 4 more constraints here. This is just getting, and actually this is a different variable. So I'll call it s. Not s. I'll call it b. B, right? I'm getting here a huge, huge, huge system of linear equations. A gigantic matrix, and it'll kind of, you know, you can see the matrix multiplication. It's just like the last video, okay? Here is our C naught, C1, C2, C3, and then what am I multiplying here? So C naught, this is confusing me, so I'm going to reverse it. Let's start with C3, C2, C1, C naught. So C3 gets multiplied by x naught cubed. C2 gets multiplied by x naught squared. C1 by x naught, and C naught by 1. And then same here, x1 cubed, x naught squared, x1 squared, x1, and then 1. But this isn't even the whole picture, because we have a different variable down here. Okay, so this is actually a huge matrix. Oh my god, so huge. So we have C3, C2, C1, C naught, and then we have 4 more coefficients for the second piece of the polynomial. So I'm going to write them here: B3, B2, B1, B0. And then we're going to have 4 more. I'm going to call them A3, A2, A1, A0. This is a huge vector that we're multiplying this huge matrix. So what do I put over here? C3 gets multiplied by x naught cubed, and then finally we get to we're multiplying the first row by this vector. We get to B3. What do we multiply B3 by? Well, B3 is not present in our equation right here. So we're just going to multiply it by 0, 0, 0, 0, 0, 0, 0, 0, etc. Okay. And then we'll have some other junk here. But then eventually we will start getting to the equation with the b's in it, and we will have more stuff. So what was here? X naught, yeah. So we're going to put x naught cubed, x naught squared, x naught 1. X naught cubed, x naught squared, x naught 1. And now over here we have to put the zeros because in this equation there are no c coefficients. The c coefficients have to get multiplied first. So you're going to say C3 times 0, C2 times 0, C1, C naught times 0, and then B3 times x cubed. Now we're starting to see this equation out. B3 times x naught cubed, B2 times x naught squared. So we're getting this gigantic matrix when we're trying to make this cubic spline. But the good news is that it has a lot of zeros in it. And zeros seriously simplify the task of solving a matrix. In reality, you're going to get all of the values in this matrix to be along this diagonal. Okay, not the very center diagonal, but they're going to be all in a stripe that goes along through the middle. And that's information that we can use to solve this matrix quickly. If we have, so we have, how many coefficients do we have here? If we have S, or I'm sorry, S is our, we have n points, let's see. We have n points? No, we have n plus 1 points, which means we have n pieces. And for each piece we have 4 coefficients, which means our matrix, you know, the size of the matrix is 4n. 4n on this side too. So that's a huge matrix, and solving a matrix is a very slow operation. If you remember from our what was the name? Algorithmic time complexity videos. What big O notation means? Solving a matrix is generally big O of n cubed, which means, you know, in this case it'll be big O of 4n cubed, and that's a nice big number. So if we know that a bunch of these are zeros, then we can solve it a lot faster, actually. And that is what is talked about here. So because of the way that we set up this matrix, let's see here. So I'm gonna skip all of this. It's pretty boring. Let's look at the matrix. It doesn't look quite like our matrix because they make some simplifying assumptions. But it does look pretty similar, where all of the non-zero entries are in the middle. And that makes it pretty straightforward to solve this matrix. Using some nice, here I think they even say it, a linear system with a matrix of this form will be shown by theorem 6.21 in section 6.6. This is section 3.5. So even they're not saying like how to solve this, at this point. They're saying, trust me, we'll solve this matrix later, but it'll be a lot faster. We could take a peek at section 6.6 if we want to. But I don't really think it's worth it. And interestingly, well, it is worth it, and here's why. This algorithm that they printed in the book is wrong. I've gone and implemented this, and I came up with, like, for the way it's printed here, I came up with the wrong answer. And I had to go and rework it. I had to go to section 6.6 and figure out theorem 6.21 and like figure out what was wrong with this and fix it. So that was fun. So solve this matrix and you get a bunch of coefficients. These are the coefficients for S1 or S0. These are the coefficients for S1. These are the coefficients for S2 and so on. And then you have your cubic spline. So because I did this for the Blue Ocean video, I actually have the source code for that, and I think for the code section of this video, I am just going to take that source code, put it into our little Math for Game Developers thingy, and then just get it working there, and use that as the example. Let's go look at it. GitHub. So now, find the part where I did the cubic spline. Where was it? Where was it? Is it in here? Nope. Maybe the search will work. Cubic. Spline.h, of course. Beautiful. Beautiful. Alright, alright. So good, it's nice, it's in its own little class here. Oh, I assume 16 spline points for this algorithm, but it's simple enough to change. There we go, Burden and Fair's numerical analysis 9th, algorithm 3.4. That's exactly what we were just looking at. Algorithm 3.4. Except with the minor change here where I discovered a mistake in the book's algorithm. Let's see, 4 minus mu I minus 1. Gotta try and find it again. I don't even recognize this. L, mu, and z. L, mu, and z. Oh, yeah, that's the error right there. So the book has 2x plus 1 minus x I minus 1 minus h times mu. I have 4 minus mu. Wow. That's very different. And here mu is 1 over L. Mu is... Oh yeah, I'm assuming h is 1. So h is... what is h? What is h? Well, hold on. Make sure I understand what H is. Yeah, H. No, 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 no. Damn it. Oops. Algorithm 3.4. Where'd it go? It's 3.2. Oh, I lost everything. There's 3.3. Cubic spline, 3.4. All right. Where were we? H. Input. And it makes the H's somewhere. Does it make? Yeah. H is x plus 1, xi plus 1 minus xi. Good. Then the H's are, and this is generally true anywhere in numerical analysis, this distance right here is h naught. This distance here is h1. H1. This distance is h2, and this distance is h3. Now, I just assumed that all h's are 1 for my algorithm. That makes it a little bit easier. So here, you have things like h over L. Oh, let's see. Oh, wait. No, that means that, that means that this is the same, because this is xi plus 1 minus xi minus 1, which is the same thing as, so let's see, xi plus 1 minus xi minus 1. So that is xi plus 1 minus xi plus xi minus xi minus 1. I've just added and subtracted an xi here, so I haven't changed anything. These are equal. And then this guy is equal to is equal to h I, and this guy is equal to h I minus 1, just by the definition of the h's that we have over here. So let's see, plus xi minus 8. So these are added together, and if we assume all the h's are 1, then that's equal to 2. So then we'll have 2 times 2, which is 4. 4. So that does match. 4 minus 1 times mu. 4 minus mu. Yeah, so that part of the equation is the same. Okay, then we have a minus z over L. A minus z over L. So that part is the same. So now we have Cj. The C's are the coefficients, so let's see. Coefficient J is z minus mu times C. Z minus mu times C, that's the same. Then we have B coefficients. What are the B coefficients? Oh, I see. So the way they have it set up is a little bit different. They just have, for each n, they have a x cubed plus b x squared plus cx plus d, or maybe d plus c plus b plus a. It just makes it a little easier to work with all the numbers. So like the kth piece, we'll just put little k's here. Yeah, that's all they're doing there. So b is difference of a's minus some sum of c's, difference of a's that could be different. I'm not sure how my coefficients map to his coefficients. Let's see. I said that 2 is C, so ABC 1, 2. So C is 2. That means 3 is D. Oh. Yeah. So here's where it starts to differ. I'm calculating my D's first. But other than that, it's the same. It's a difference of C's over 3. So here's the over 3 part. And here's the difference of C's part. And then we have here a 1, so that should be a B. X minus xj plus 1. See, my points are my x's, right? Xj plus 1 minus xj. Yeah, that's completely different. It's completely different. So yeah, my algorithm is definitely a little bit different from his. And when I copied his, it basically didn't work at all. Which is fine. Good. And we're going to ignore this integrate part. I'll get to that in a few future videos, what the integration is. And it's not actually an integration. It is a quadrature. Why'd I call it an integration? Because, you know, it is technically an integration. It's just the word integration is overloaded in numerical analysis, so we like to use quadrature instead. But I didn't here because I'm dumb. All right. So let's see, we calculate the new coefficients. Okay, good. So this will work for our purposes. And let's just start coding. Let's just start coding here. Let's make a spline. Let me think for a second about these H's. Let me think. Okay, I am going to explain what happened with the integration here because it's part of my thinking. What I did was, there's a problem where you have a camera here, if you have a point along your path here, and then a point here, and then a point here, and then a point here. So this is T0, this is T1, this is T2, and this is T3. So then you have your object moving along the path, and you want it to do something like this, and then swing around. You know, nice, well, all right. We'll just add another point right here so that looks better, because I completely missed. All right, here's T3, or here's T4. So you have your points that you want your camera to go along this path. That's all in good. Except that if you say that the time interval between all of these are the same, then that implies that the camera has to speed up to get to this point, but then it kind of lollygags around in this point. I'm not sure what happens there. I think if you do that, it might even, this would be interesting to experiment with. I think it might, because it has like, you tell it that no wait, you don't tell it that the derivatives should be constant, do you? You tell it that the derivative on this side should be the same as the derivative on that side, but you don't say that all derivatives should be the same as each other. So that means that you start out really fast, and then when you hit this guy, he's got to cover much less ground in the same amount of time. So now he's going to be going really slow. And then he's going to start speeding up, and now he's going really fast again. And when he hits T3, now he has to cover the same, much less ground again, so he's going to start going really slow. To solve that problem, I did a quadrature.
I'm not going to get into what that, we'll cover that in a future video. But I made it, I looked at the arc length of this curve, and I said, okay, forget where the points are, just force it so that you always go a constant length, a constant distance along the curve over a constant amount of time. Like I forced that, I hard-coded it. Using a quadrature and, you know, an arc length algorithm, a formula. So I did that, but now I'm thinking maybe I could have avoided all that pain of the quadrature by just screwing around with the h's. So have, like, instead of T0 and T1 and T2 be all constant time intervals, in other words, all of the h's are 1, maybe you put a lot of time here and only a little time there, and then a lot of time here and a little time there. And then it knows that, okay, I have a lot of time to cover this big distance, and then less time to cover the small distance, and then a lot of time, and so it can kind of keep a constant speed. That may be an approach. I feel like I could get that working if I looked at it a little bit more. But I want to use, I think I want to keep using this, even though, you know, this constant interval way of doing things, even though it may not be the best way of doing things, because then next video I can use that to teach quadratures. I can say, well, you know, now we have this problem where the thing goes really fast and then slows down, and then we're going to use a quadrature to fix that. So that's what I want to do. I'm going to get some water real quick, and then we will start the code portion of the video. All right. Let's take a look at some code. I'm just going to take this cubic spline. Oh yeah, look at that, arc length integrand. Copy and paste, math, new file, paste, save, spline.h. It's so beautiful. Okay, so let's see here. I don't know what mess I was doing before, but we want to take that out, and we're going to build it. All right, built. And let's go to that folder, debug it, make sure it's working. Oops. And it's working. Okay.
These guys, I feel like will be distractions, so let's get rid of them. Let's get rid of... Oh, this is too much stuff open. All these tabs are distractions. And this, and this, and that. Then we'll keep that. Get rid of all this stuff. Okay, we can get rid of the monsters. How do we... What was it? Create character. Still want to create the player, but now we will get rid of the monsters. Caps lock went on somehow. Alright, monsters are gone, and we'll get rid of this seaweed because it is also a distraction. Seaweed. Comment out the seaweed. Oh, nice. Very cool. You know what? I just commented out the initialization. And so it's just a bunch of junk data now instead of actually having removed them. Yeah. That's awesome. And I'm glad we did it. But let's take them out for real. Yeah. See, I just didn't set the positions, and so there's just a bunch of junk data in there. So let's see, how do I actually take them out? This is where I draw them. Oh, yeah, I know how to take them out. I know how to take them out. This thing right here, oh. Seaweed.h. Num seaweeds. Yeah. We're going to set the number of seaweeds to 0. And that should get rid of the seaweed. There we go. Back to an empty canvas. So now instead of seaweeds, I want to have splines. So we're going to go here and we're going to create an array of splines. Hello DD410, thank you. And hello Judelco TV. Crazy seaweed. So what are we doing? Creating some splines. What does it want me to pass in? A bunch of points. And it will calculate a bunch of coefficients. So I pretty much need 16 spline points. Include spline.h. Oh. I'm going to have to change these vectors to the vectors in this format. So this may take a little bit of porting code over, but that should be fine. So what's the actual vector format? Vector, capital V vector. G spline points, and we'll have spline points of them. Does that build? It won't. It won't build. It built. How did it build? I have the wrong... Oh, you know what? You know what? I know why. Because I did this. Awesome. So I put in this define here from when we did the seaweed, define vec3 to vector. And I'm porting the same code over, so it's still using that define. So this is super hacky, guys, but that's fine. Oh my god, I do some Newton-Raphsons. That's crazy. Yeah, I'll definitely explain that another time. Okay. So we have a bunch of spline points, and
there are 16 of them. So let's just go ahead and make this array. I don't even have to do it here. I can do it right here. Let's do it right here. We'll make the first one at 0, 0, 0. Let's see, 16. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. So that's 16. Let's make them go in a more or less straight line. That'll be our first pass. 10, 11, 12, 13, 14, 15. Let's make them a little wavy for now, because I'm gonna put in some code to render them, and I just want them to show up. So now there should be some kind of render or draw function here somewhere. Here it is. And where do I render the seaweed? Render the seaweed. It's pretty much the same code to render this stuff as to render the seaweed. I'm gonna borrow that code. I'm totally gonna borrow this code. Let's make a new scope and copy this code. Paste. Okay, so what's going on here? So if I recall, I had one my nose is extra itchy today. I had one loop to draw the boxes that were the little lobs on the side of the seaweed, because I just copied that code over here. And then I had another loop to draw the actual lines, and we'll keep both of those, except now we don't want to have this offset vector anymore. What was that offset vector? Yeah, that should basically be 0. No offset. And what is the seaweed thickness? Seaweed thickness is 0.03. So I'm just going to copy this in here, and then now I'm going to say spline thickness. Oh, we have a new array, spline points instead of seaweeds. So, oh wait. There's a bunch of stuff named gSeaweed, so let me, oh yeah, no, this is fine. So select all of these, and then say, now it's spline points. And I can get rid of anything that says this. Actually, yeah. I had a bunch of different seaweeds, but I only have one spline now, so that's why I have 2 loops. I need to simplify that to 1 loop. So take out the end loop. And then I need to fix up this mess. All right. So let's take out this loop. This code is so gross and dirty. That's okay. probably also going to be buggy. Oh my goodness. Oh, this code didn't even get used. All right. So let's see, spline thickness 0.03, and then we draw a box in the center of the spline. Is it a scaled box? Where does this scale ever get used? Oh, Christ, it doesn't. Oh, forgot a semicolon. I don't think the scale ever gets used. It doesn't. And the thickness never gets used. That's awesome. That was some janky code, but we've simplified it a lot now. And let's see, here we go. There it is. There's our nice line. Wow. I don't know if you guys can see it, but the line looks really weird between... Yeah, I think you guys can see it. The line looks really weird here. I'm not sure why. And it seems to go way too far into infinity. I don't think it's supposed to go out this far. So, something's wrong. And I think I know what it is. Let's see. Size of spline points. We know how many spline points we have. So let's just say we don't have to calculate the size of the array. We can just do that. That didn't fix our problem though. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. So this is the problem. It's an off by 1 error here. Each time we draw a line, we need to draw it from our current link position to the next link position. So we want to stop short of getting to the very end, because if we're at the very end, there is no next link position. So that is an off by 1 error, but it should be fixed now. And it is. All right, cool. So this is actually not all of what we need. Actually, this is a really bad way to draw the spline. Yeah, I'm gonna comment these out. We're gonna draw the spline a different way in a moment, but we have to calculate it first. So let's see. You know what I should have done? Yeah, that's what I should have done. All right, let's do that now. So now we're gonna do all this when we're loading. So we're gonna say mPoints equals those points. So that should be good. Do we calculate the lengths? We do calculate the lengths. Good. Actually, we don't want to calculate those lengths. Do we? Oh yeah, okay. We're just gonna do this. Yeah, that's fine. Okay. never mind that now. So then we can say gspline dot initialize spline. All right. Now in our draw function, instead of drawing these tiny little these lines between each link, we're going to break this into a little bit more granularity. Actually, should we use a float, an int here, or float? Should use an int. Yeah, let's use an int. In general, I don't think it's usually a bad idea to use floats as in the control part of your for loop. We're gonna use ints. Spline points, but we're gonna say okay. So here's what we're doing. We want to trace a path along the spline, but a much higher resolution than the actual number of splines. Here I'm doing it only at the resolution of the number of splines, but obviously we need to draw it at much higher resolution than that if we're going to be able to see the curviness of the spline. Otherwise, there's no point to do this. So let's do this. Float what frames per second do we want to draw the spline at? So 60 frames per second. That means we need to draw 60 times between each spline point. I should say this instead. I should say seconds per spline. Seconds per spline? Yeah, we'll do that. Seconds per spline. And then no, not seconds per spline. Segments per spline. So here we go. Segments per spline. So now we have this t parameter, which is going to be how far we've progressed along the spline. And when t equals 0, we're at the start of the first segment. When t equals 1, we're at the start of the second segment, and so on. So now we get to do gspline.spline at time t. And that will give us back a vector. And now we have to do this again. See, this is what we need to do. We're going to have a t0 for the current time and a t1 for the next time. And if I don't do -1 here again, we're going to have the same problem as we did last time with the off by 1 error. All right, good. So with t1, we're going to add 1 to k, so we're going to get the next segment position. This is a little bit of duplicated work because we're calling spline at time twice for each location along the line. We should really cache that off, pre-calculate it and save it somewhere, but whatever. This is just testing code. Learning code. Doesn't have to be fast. So now we can just say Draw the lines. Compile. Oops. Not assignable. Bullshit. Okay. Yeah, see, this is an array of 16 and vectors, and that is an array of 16 vectors, but it doesn't want to copy them because, I don't know, it doesn't like copying arrays. That's fine, we'll just do a mem copy here. Oops. Oops, 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 oops. We'll just copy the memory, which we know that we can do because this is a simple data type. It's just a vector, 3 floats each. We're copying an array of 16 vectors to an array of 16 vectors. It shouldn't be any problem. Let's do it. And there we go. Oh yeah, so already we have some nice properties, except that, oh, yeah, it's looping it back around to the beginning for some reason. I'll worry about that later. But you can see that the line is nice and curvy now. So that's working, and that's good. So that's some progress right there. Let's now come up with some new initial points that are maybe a little bit more interesting. So let's do 10, and then 10, and curve around like this, 10, 10, and then we'll do 30 and 20, and then we'll come back and then say 15 and negative 10. We're going crazy, and then negative 30, and then back to 10. And then we're going to have negative 31 and 11, because, again, getting crazy here. Oh, wait, you know what? I don't want to do it this way. I forgot that the up-down vector is y. So I'm going to do that. I'm going to do like that. Oops. 0. So good. We're going to keep them all at the same level. In fact, let's bring them a little bit up off the ground. Let's keep them all flat just for make things simple. Good. And I don't know, yell out some numbers in the chat if you care to. 5, and then negative 10, 0, and then negative 10, negative 10, negative 15, 50, oh my god. $10, 40, I'm like having serious trouble coming up with more random numbers. 30. Let's do like a regular pattern here for a little while to see what goes on. 40, 10, and then juke back around to 15. 15. I don't know. That looks about good. Let's work with that. Unless anyone shouts out some crazy numbers. And we have a bug. All right. Run that. Whew. So here we are. Wow. This is one crazy spline that we've made. This is interesting. Does the spline cross itself? We have an orphaned spline point. That shouldn't happen. Let's change these up a little bit. I don't like that. So 0, so we start at 0, oops, what's going on? We start at 0, 0, and then we get 1 a little bit. Yeah, let's change that one. Let's change that to 5, 0. Okay. Then we hit 10, 10. All right. Okay, I think here's what's going on. I'm going to change this one too. So this is 0, 1, 2, 3. So 0, 1, 2, 3. And I'm going to make it more in this direction. Less in this direction. 15. I'm just trying to differentiate things a little bit so that we can tell what's going on. Also kind of want to figure out this weird bug, how it's drawing the line the wrong way. Okay, that's a little better. It's drawing this line wrong, and I'm worried about that. So it starts here, it comes this way, curves around, big looping curve till it hits here, comes back, oh yeah, hits this one, but now its velocity is so high it's got to shoot past and come back. I'm going to come over here, over there, over here. This is pretty cool. And then it enters that constant, roughly constant section that we made there at the end. But notice how it doesn't move in a straight line, even though we have 4 points in a row, because the points outside of the constant section are affecting the constant section. So that's pretty cool. And then we loop back around to the left, and then we hit this last point right here, which it shouldn't do. 1, 2. Let me look at what that last point is. I'm going to change that last point. 15, 15. I'm going to make it negative 15, 15. Or no, 15, negative 15. Just to try and get it away from the other point. So yeah, now here's that last point right here. Okay, so that's why it's I think I know why it's sending it back like that. It's just like sending it back to the origin just before it's about to hit that last one. So that's just a little rendering bug that we have. And how do I fix that? Spline at time, spline at time. That is probably a bug in my spline at time formula. Yeah. Yeah, it's walking off the end of that array. So let's do this. If spline is bigger than or equal to the number of spline points, spline equals the number of spline points. And we can probably do it the other way too. If spline is less than 0, spline equals 0. Just clamp it. Just clamping it. And that won't fix the bug, will it? Nope. Here's what we need to do instead. If t is bigger than spline points, t equals spline points. And this is going to be a hack. If t equals spline points, t equals spline points minus a very small amount.
The reason being that if t is exactly equal to spline points, oh, it's not rebuilding. If t is exactly equal to spline points, then it's gonna, it's gonna be another little off by 1 error. It's gonna try and get this. It's gonna try and be 0 on the very next spline point. Shouldn't it be spline points minus 1 times? Maybe it should. No, because then, well, let's try that and see what happens. If we do this, then I don't think it will draw the last spline at all. Let's see what that looks like. Oh, wow, it looks the same. Awesome. So what is this? Go away. Oh, you know what? I think you are right. I need another -1 here. There we go. Should be drawing that last little bit, though. Okay, I'm not even going to worry about that. 0.1 errors are lame. Okay. Okay, anyway, we have a spline. We have a spline. I'm going to do one more fun thing, which is I'm going to draw a little box that travels along the line. Spline at time. I'm going to use fmod. I'm going to use the current time. How do I get the current time? And I mean like the game time. How do I get the game time? Application get time. Application. Come on. Here. Application get time. And then we can see how it changes velocity as it goes. And what am I modding it by? Spline points. So I'm going to pump this fmod into gspline dot spline at time. And wait, what? Okay. I deleted the wrong thing. All right. So we're just going to draw a little box that goes along the spline. Oops. There it goes. Yeah, we could definitely see it speeding up and slowing down. Totally. Oh, did you see that? Oh, did you see that? It walked the first spline twice. Me and these damn off by 1 errors today. Am I right? Let's divide this by 2 to slow it down a little bit. Let's also, so that we can see more clearly what's going on, this section that's is like the constant time section. I'm going to slow down a little
bit. I'm going to do this. I'm going to make it a really compressed constant time section so you can really see what's going on. All right. So we're starting off slow, and then we get to sections of the track that have a long time between spline points. Then we start to slow down, and then we speed up again, or other way around. Yeah, you get what I mean. Oh wow! Oh wow! Look at that! Oh, that's interesting. Yeah, that's cool. All right. So when the spline points are close together, our little guy is going slowly. And when the spline points are far apart, he is going quickly. So that's maybe something you want, but maybe something you don't want. So the reason that this craziness right here is happening is, like I mentioned before, let me just add some more parts here. 13, 12, 14, 11. I'm going to add more parts to this. So this should be 10. So we can see, so we can really see what's going on. 9 and 16. Yeah. And then we'll make this a little more drastic. 30. It's going to be totally great. Not as cool as the seaweed, but. So we start off slow, and then we get a little more speedy in the big sections of the track. And now we're starting to slow down a little bit more. Yeah, that's good. When we get here, oh, now we're going to go super slow. Super slow. Super slow. Super slow. And then over there, they get farther apart, so speed up again. Great. So our splines work. Ladies and gentlemen. In fact, I'm just going to keep adding sections to this part because it's really cool. Okay. Let's add one more section. 17. See what happens. So like we have some amount of like stability that it's happening. You can tell that in the part that is closest to the edge, the crazy spline points outside of our straight part are affecting what's in the straight part. But it affects less and less as you go to the center. So starting again from the top, we can see, oh, look at that. It's affecting it less and less. I'm going to add another one. So there's 7, there's 18. How many points do I have to add to the straight section before the straight section just levels out entirely? And, I've added quite a bit many points now, and it still hasn't leveled out entirely. So that's interesting. I'm going to add one more. Now it happens. Yeah, this is maybe almost completely leveled out. Maybe it's still kind of curvy. Well, you can really see the difference in speed though, right? He's super slow right here. Super slow. Can I move the player along the spline? I probably could, yeah. Let's see. Want to try that? I want to see him go around one more time before I do that. Super fast. Super fast. Super fast. Putting on the brakes. Putting on the brakes. Very cool. All right. Putting on the brakes. Let's move the player. So I guess really simple way to do this. Every frame, I'm just going to set the player to go to be, let's see, set translation of the player. Instead of having it be the movement and velocity and all that, I'm just going to say mh player set translation. So instead of getting it from movement, we're going to get it from gspline dot spline at time. I'm just going to go and copy this other stuff that I wrote before, or else I'm bound to write that same off by one error again. Just know it. Okay. So let's do that. So I should still be able to look around, so it'll be kind of like an amusement park ride. All right, here we go. It's not cool enough. It's not the same if you don't like make sound effects. So I gotta make sound effects. Now it's the slow ride. Now we're like going up the. Oh my god, should make a roller coaster sort of. It's the boring part of the roller coaster where you're just going up, and now we're going over the edge. Oh. Okay. Fun with math. All right, cool. I know something we can do. I'm gonna go back to having autonomy over here. And I'm gonna do this. I'm gonna make a train. Now you can really see how they spread out at the fast parts. Roller coaster simulator, yep. I think I'm going to take some parts out of the slow part here because it takes forever to get to this slow part. And then we'll actually go back and record the actual video. How about that? Let's see, all the way up to the top. And let's see. What were these before? I don't remember. That doesn't matter. Negative 40. 19 is fine. And then 20. And then we'll go with 5. So I took two points out of the slow part. Out of the slow linear part. Let's see how that looks. Yeah, that'll do. No, I don't like this. I'm going to put this guy. Where is he? This guy? On the other side. Just want it to be like fairly clear what's going on when people see this. So I don't know. Maybe I'm being too picky here. There we go. This part of the track. Oh wow. We got a little loop-de-loop right there. So I just want enough variety in my, in my roller coaster, my spline coaster, to be able to demonstrate everything that a spline can do. All right, this is good. Okay, so what now? Now we have the code portion of the video written. So it's time to record the Blackboard part of the video. And what example should I use? The camera example, like, it works, but it's not the best because cameras are maybe kind of boring. They're essential for good video game design is to have a good camera design, but they're kind of like boring. And now that we've discovered this roller coaster thing, it's a lot more interesting. I kind of like it, and I think I'm going to use the roller coaster example instead of the camera example. So you want to build a roller coaster, and you don't want to have to nail down every piece of track, so you just want to be able to specify these little sections and then do cubic interpolations between the sections to generate the rest of the curve. And that's what a spline is, and then I can go about showing how all the constraints let you specify the spline by setting up, 16 coefficients, 16 constraints, get a big matrix, solve it. It's mostly zeros. The solution, the algorithm for solving it is a little bit nicer since there are so many zeros, but it's still, I don't think, worth explaining. Yeah, that's good. Let's give it a shot. Oh, you get more sleep, man. GDC next week, am I right? I'm not gonna get any sleep during GDC, so I gotta get sleep. I gotta get all my sleep this week. It's actually not true. I don't lose sleep for GDC. I go to sleep at a nice early time. Same time I go to sleep every night, even though I'm at GDC, and I feel great during GDC. And everyone else is like, I'm so tired, I didn't go to sleep last night because I was at a party. And I'm just all, I feel great, dude. It's 8 a.m. Let's do some stuff. Let's learn how to make games. Let me get some water real quick before I do that. Turns out talking a lot dries your voice. Who would have thought? That's really messy. I want to rewrite that. Yeah. Cubic splines. So, Camtasia. Start recording. Here goes. Take one. It's always the crappiest take. In fact, I'm not even going to record. Stop recording. Delete. We'll just do a dry run. Okay, welcome to Game Developers, yada yada. Let's say you want to make a roller coaster, and it should look like this. It's a crazy roller coaster that's not possible in real life. But you don't want to have to specify in your game where each and every one of the, these points on the roller coaster is. That would take forever. So instead, you just want to specify where all of the important parts are. Just like that. We're going to just specify these points, and then we're going to do cubic interpolation, piecewise cubic interpolation, between all of the other points. Should probably explain that piecewise means that between any 2 points you have a cubic polynomial. And then the complete curve is just a collection of cubic polynomials. It itself is not a cubic polynomial. I don't even know if I have to define the term piecewise. I think it's pretty self-evident what piecewise means. Maybe I should just avoid using it. It's like one of those things where my math degree is getting in the way of my communication. Piecewise, just going to try and not use it. Okay. So we want to make a cubic splines, which is a bunch of cubic polynomials put together end to end. And we also don't, but the problem is that last video we had a constraint that, now I have to go see how I wrote it in the last video. So that was important. How I wrote it, I want to write it consistently with how I did it last video. So H. My function was H? Why did I use H? Oh, that's awful. H's are the distances between my x's. Well, I'm not even going to mention that. I'm going to assume a constant distance between all of my x's. Yeah, that will be fine. I'll just do that. I don't even have to introduce the h's. I should probably make them f's anyway. I'm going to use f instead of h. I don't like. I want to keep the letters the same if I can, but whatever. This is a function of time. Okay, where was I in my explanation? I don't remember. Everything is. This is why I do the practice tape. This is why I do it. Okay, that's right. I remember. I recall. So for the cubic spline we had last time, we decided that at f of 0 and at f of 1, at time 0 and at time 1, we wanted the derivatives to be 0. But if we did that, then our roller coaster would stop. And we don't want our roller coaster ever to stop. So we're going to have a little bit different of constraints than we did before. What the hell? I hate it when it does that. Okay. So different. We're going to have some different constraints than we did before. What else do I have to explain here before I really get into the gory details here? What else do I have to explain? Let's just start again from the beginning. I'm going to need to do this a few times anyway. I just got to, build up a head of steam before we really start cranking here. Welcome, Math for Game Developers, yada. We are going to make a roller coaster. It's going to be an impossible roller coaster that looks like this. Well, no, I guess you could have a roller coaster like that. That's fine. But we don't want to specify every point on the roller coaster. We're just going to specify the main points, and they're going to look like this. These primary points here, and then we want to write an algorithm that does interpolation between all of these points. And we're going to use an algorithm very similar to the cubic interpolation method that we did last video. However, won't be exactly the same, because if you remember last video, if this is our function f, okay, at each time, let's see, if this was f0 and this was f1, we wanted the derivatives at each of those points to be 0. And if we do that same thing now, then our roller coaster is going to stop when it gets to each one of these points, and we don't want that. So we're going to have a little bit of a different formula that we construct this time, because we never want our roller coaster to stop. But we do want it so that I didn't explain this time, after I started from the beginning, that we're going to have a bunch of cubic functions and we're going to stick them together. I have to remember that. I should probably take notes or something. So we want the derivative at the end of this section to be the same as this derivative, which is like the speed, at the beginning of the next section. And we want the acceleration at the end of the last section to be the same as the acceleration at the beginning of the last section. So we're starting to get a lot of constraints here. For our roller coaster. And we have to make sure that the number of constraints we have is the same as the number of coefficients we have in our cubic polynomial. Now each section has 4 coefficients, so each section should have 4 constraints. So what are they? Let's see, 1, 2, 3, 4. Yeah, 1, 2, 3. Sorry, I'm just going to do some counting to myself real quick. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. Yeah, all right. So when time equals 0, we want the train to be here. When time equals 1, we want it to be here. When time equals 2, we want it to be here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 constraints. And they're all going to look something like this. At time 0, we want our function to be equal to some value. At f1, we want our function to be equal to some value, and so on. We also want the speed here, the speed as you are heading into this point, to be the same as the speed as you're heading out of that point. And the acceleration when you're heading into that point, the same as the acceleration when you're heading out of that point. So that is 1, 2, 3, 4, 5, 10 more constraints. And they're going to look something like this. The speed at time 0, I have to use a different notation here. I have to use something. I don't want to use the S notation that I was using earlier because it's kind of throwing a curveball in there. So I'm going to use F1, F2, F3. Just have to be really careful to talk about. Here's F1 of X. Or F naught. Here's F1, and so on. 1, F2, F3, F4, and here's F5. F5. I have to be really careful to explain piecewise. All right. Good. Good, good, good. So now over here I can say the derivative of f1 at 1 should be the same as the derivative of f2 at 1. And the acceleration of f1, I should use speed and should I? Should I say speed and acceleration instead of derivative and second derivative? Can probably just be redundant and say both. And then I'm gonna have two additional constraints, which is that the acceleration at time 0 should be 0, and the acceleration when I'm done at time 0, 1, 2, 3, 4, 5, 6 should be 0. So that's two additional constraints. So we have 24 constraints total. Now in the last video, we put these constraints together and we found a very simple system of linear equations that we could solve. Our system of linear equations will not be nearly so simple this time, but it will have some properties that will let us solve it more easily. And I'm going to try to draw what the matrix is going to look like for you. So here are the coefficients that we're solving for, just like last time. Let's say that f of x is ax cubed plus bx squared plus cx plus d. And we're going to need some subscripts here. If this is the kth section of our cubic polynomial, then this is going to be ak, bk, ck, and dk, just so we can differentiate the coefficients of each section. So then we're going to start with a naught, b naught, c naught, and d naught. And then we're going to have a1, b1, c1, and d1, and so on. And then over here on the left, inside our matrix, we're going to have x naught. We're going to, maybe I won't even draw out the individual things that you multiply. We're going to have some coefficients over here that multiply, not coefficients, these are the coefficients. We're going to have some values over here that multiply into these coefficients. And then we're going to have some values here that multiply into these coefficients. And then we're going to have some values here that multiply into those coefficients, and so on. And everything outside of the boxes that I've drawn will be 0. 0, 0, 0, 0, 0, 0. So we end up with a very large matrix, a 24 by 24 matrix. And normally large matrices are difficult to solve, but because it has so many zeros, it makes it very simple to solve. We generate something called a tridiagonal matrix, which means that there are just 3 diagonals going through the center and everything else is 0. And there's a nice fast algorithm that solves tridiagonal matrices. Now I'm not going to cover that algorithm because you don't want to be implementing it yourself. It's kind of crazy. In fact, even the book I got this from implemented it wrong. But I've provided a spline implementation for you in the source code, and we are going to go look at that. And then we go to source code section, and we see the amazing, it's actually kind of simple, not very amazing at all, and I wouldn't recommend you use it for an actual program, but it is a spline implementation, so probably shouldn't sell it up so much because it's crap. But anyway, maybe I should go into a little bit more detail than this. Yeah, I feel like actually writing out 1 or 2 of these constraints so that we can see how it goes into the matrix. How important is it to actually be able to write this? Like, I don't know. I'm definitely not wanting to go over solving a tridiagonal matrix. That is a pain. That's something like, I feel like as long as you know the basics of how cubic splines are constructed, why they're used, what they're used for, that's enough. Because if you want to know it at a deeper level than that, honestly, you should just go read a numerical analysis book. It's easier said than done, obviously, but these things are kind of intense. Should I at least talk about how these simplifications are done? Okay. Uh-oh. Let me see real quick if that person is important. I don't know how many times I've gotten interrupted in the middle of recording. In fact, it happened once on stream. Get phone calls and texts and stuff right in the middle of recording a video, and then I have to start over. Always when it's my best take. Always. Yeah, these manipulations are kind of boring. I could do them, but I don't think they teach you anything about the underlying, about cubic splines. They're just simplifications to make it into a tridiagonal matrix. Yeah, because the way I've drawn them here with the boxes, they're not quite tridiagonal. These boxes are 4 by 4. And then you do some simplifications to make them into tridiagonal so that there are only values in 3 diagonals. And then you get a matrix that looks like this. 1 diagonal, 2 diagonal, 3 diagonal, tridiagonal matrix. And yeah, that's fine. That's okay. So let's do that. But I think I will write out 1 or 2 of the equations so we can actually see what's going on. Let me save this file, save, and then export it and move it to my second monitor like the cheater that I am. And ooh, my second monitor is now being used for something else. Okay, hold on. How do I move this to my second monitor? Can I email it to myself? Okay, put it in my Dropbox. I got a new computer, and the second monitor is now on the new computer. And I don't have Dropbox set up or my email. Let me just log into my email real quick. Sorry about this. Okay. And now this guy right here. email to myself. Drag this guy in there. Hit send. And there it is. Is it there? Waiting for it to show up. There it is. All right. Second monitor activated. Let's clear this junk away and do an attempt at recording a wonderful video on cubic splines. Microphone check. Microphone check. Seriously? Where's my microphone? Have you guys been hearing me this whole time? Oh, there it goes. What? Check. 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 Oh my god. Been using the built-in microphone this whole time? This guy's not even plugged in. Amazing. So amazing. Okay, what is this?
There we go. Is it better?
Is it better?
Yeah. Okay. Now it's using the right microphone. Okay. Let me come over here. Okay. Let me check to see that OBX is using the right microphone too, so that you guys can hear me in all my glory. I have no idea how to do that. There we go. That should do it. Hopefully I don't have to restart the stream or anything for that to...
Is it working?
Yeah, totally. Okay, good. Alright, so microphone is set up. Microphone is ready. I feel like doing an audio test because my levels are not so strong here. Well, yeah. Let's do a quick audio test. Welcome to Math for Game Developers, where today we're doing cubic splines. This is a roller coaster. We're gonna make a spline for our roller coaster, or we're not because this is an audio test. Recording videos, guys, it's really exciting. Today, we're doing cubic splines. Yeah, that's fine. Yeah, that's good. That'll work fine. Okay, don't save. Alright. We're bringing up the cheat sheet. We're starting the recording. Welcome to Math for Game Developers. Today we are going to make a roller coaster. And we're going to use the same methods that we used last time, where we're going to do cubic interpolation between all of the little parts of the roller coaster, because we don't have to specify every single part of the roller coaster. Instead, we're just going to do cubic interpolation between this part and that part, and then between that part and this part to get this curve, and so on. That's called piecewise. We're going to do piecewise. We're going to make a piecewise function or something like that. I don't know. Starting over. A lot of times I get off to like 3 false starts where I get 20 seconds into a recording, and then I kind of build up a head of steam and I just go from there, but you know. Oh, it's already recording. Okay. Where was I? Welcome to Math for Game Developers, where today we are going to make Roller Coaster Tycoon 2016. And in order to do that, we have to specify some points for our roller coaster track. Our track should pass through this point, and this point, and that point, and this point, and this point here, and then finally go through this point. But we would like it so that we don't have to specify every single point along this curve. We can just give it the important points, and then it interpolates the rest for us. And we kind of did that yesterday, where we had some cubic interpolation. We had 2 points, and we asked, we did some cubic interpolation between those points to get a nice soft curve between them. And that worked great. So maybe we can take some kind of approach like that. We can say, well, do a cubic interpolation between these 2 points, and then again through these 2 points, and then again for these 2 points, and then so on. And that would work, except that if you remember in the last video, we said that the speed at the beginning and at the end of our cubic interpolation should be 0. But we don't want our roller coaster to completely stop every time it hits one of our control points. We want it to keep going at whatever speed it's going at. So we can still use cubic interpolation, but we're going to have to change the function a little bit. We're going to have to change our algorithm a little bit to get us a roller coaster that doesn't slow down. So let's see how that's going to work. First, like I said, we're going to make a function between these 2 points, and I'll call that function f0 between these 2 points, that specifies a cubic interpolation just between these 2 points. And then another function, we'll call it f1 of x between these 2 points. This is called piecewise. Okay, we're going to make a piecewise cubic function, which is a bunch of cubic functions that are added together end on end. And each cubic function is going to look like this. So like fk, the kth cubic function, is going to look like this. We have ak, that's a coefficient, times x cubed, plus bk times x squared, plus ck times x plus dk. And we're going to have, let's see how many we have in this case. 1, 2, 3, 4, 5. We have 5 of them in this case, so that'll be f0, f1, f2, f3, f4. So since we have 4 coefficients per function, 4 coefficients, and we have 5 of these functions, that means we have a total of 20 coefficients. Coefficients that we have to solve for in order to figure out exactly what cubic splines we have to use. So let's get started here. What are these coefficients going to look? What are these? How are we going to solve for these coefficients? In fact, it's going to be a method very similar to what we did last time. So first we say that we have these points. Oh wow! You know what? I need to start over because I need to use t's instead of x's because I want to use x's for something else. Yep, I need to start over. Yep. Well, that was a much better take, so that's encouraging. But I'm going to start over and use t's. So I need to use the concept of time instead of, to specify. Okay. I mean, it's like what we've been talking about in the stream before. At time 0, you're at this point. At time 1, you're at this point. And then the values, the locations you're at are going to be the x's. Okay, I can do that. All right, starting over. Welcome to Math for Game Developers, where today we are going to make a roller coaster, and it's going to look something like this. And because we're pro game developers, we don't want to have to specify every single point where the roller coaster goes through. So we're just going to specify the important points like this. These yellow points are the control points for our roller coaster curve, the curve that defines where the roller coaster will go. And we want them to be nice, smooth transitions between each point. So let's see, how are we going to do this? Well, last time we used cubic interpolation to get smooth transitions between 2 points. And so let's just keep applying the same good idea. We're going to get a function, f0 of x, that is a cubic interpolation between these first 2 points. And then another f0, and then another function, f1 of x, that's a cubic interpolation between these 2 points, and so on and so on. So we'll have f0, f1, f2, f3, and finally f4. And let me really quick, actually, I almost forgot, make these t's. So this is a function of time. Okay, and this is time. So at time equals 0, our roller coaster is going to be here. At time equals 1, it'll be there. At time equals 2, 3, 4, and then finally at time equals 5, we're going to get to the end of the F4 section. So let's see, we have 5 cubic interpolations denoted by F0, F1, F2, F3, F4. And so okay, let's see here. Let's write out what each of these f's look like. F of t is going to be a cubic function, which last time I used c's, but now I'm going to use a t cubed plus b t squared plus c t plus d. Okay? And because I have a bunch of these, I'm going to add these little k subscripts. Okay, that means the kth one. So there are 5 of these, so that'll be f0 of t is equal to a0 t cubed plus b0 t squared plus c0 t plus d0. And then f1 t equals a1 t cubed. So this is just a way of differentiating all of the coefficients for each formula, okay? All of these coefficients are going to be unique. Now, just like in our previous video, we have to solve for these coefficients using the constraints that we know that our system has. So for example, we know that for f0, we want at time equals 0, which is the beginning of the f0 section, we'll call this point x0. We want the roller coaster to be at x0. And then at time equals 1, we want it to be at x1. And at time equals 2, we want it to be at x2, and x3, and x4. And then finally, at time equals 5, it should end at x5. Okay? So that gives us a lot of constraints right there. Let's see. So f0 at time 0 should be x0. And f0 at time 1 should be x1. Now the next section, f1, at time 1 should be x1. At time 1 should be x1. Time 1, x1. And then at the end of that section, which will be time 2, it should be at x2. So at the end of that section, which will be time equals 2, the position of the roller coaster should be x2. So we're going to get a lot of constraints this way. We're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this right here will give us 10 constraints. But how many coefficients do we have? We have 5 formulae. Let's do this. We have 5 formulae, and each one has 4 coefficients. That's 20 coefficients, and we need exactly as many constraints as we have coefficients. So we need more constraints. If you are wondering why we need as many coefficients as we need constraints, go and watch the previous video, and I'll give a crash course on that right now. We're going to make a large matrix that has 20 rows and 20 columns. And so we need to have, we need to have enough data to fill in that entire matrix so that we can figure out, so that we can solve this system of equations. So we only have 10 constraints and we need 20. Well, that's fine. So we still haven't specified what the speed and acceleration of our roller coaster at each point should be. So let's go to a new color and start talking about that. For f naught, okay, the speed, the first derivative, or the speed, at the time 1, in other words, when the roller coaster is here, should be the same speed as the next piecewise function has at that same time. So that's another constraint. And mind you, we're not really saying anything here that's not obvious. The speed going into this point should be the same as the speed coming out of this point. The speed when the roller coaster leaves the section F0 should be the same as when the roller coaster enters the section F1. So there should be no abrupt changes in speed. And it should be same with the next section. The speed as we're leaving the next section should be as same as the speed when we're entering the next section, and so on. So that will be 1, 2, 3, 4 additional constraints. And then we're just gonna do the same thing with the acceleration, which is the second derivative. The acceleration when you're leaving the first one, the first section, should be the same as the acceleration when you're entering the first section. So that will get us another 4. So we're up to 18 and we need 20. And we're just going to say that we can specify an initial acceleration, and we'll make it simple, we'll make it 0. And a final acceleration. This is the acceleration right here at time equals 5 of the F4 section. It should also be, that acceleration should also be 0. So there is the last 2 constraints that we have. So at this point it gets hairy. We have 20 constraints and 20 coefficients. And if we put all of that together, we're going to get a big 20 by 20 matrix, and it's going to look something like this. Okay, similar to how we did it in the previous video, we're going to have our coefficients here, A naught, B naught, C naught, D naught, and then, so in the previous video we only had coefficients for one equation, but now we have a bunch of equations, so we have to keep writing A1, B1, C1, D1, and etc. But what happens over here? When you go to multiply this matrix, you're going to have a bunch of t's here, right? So you're going to have a t naught cubed, t naught squared, t naught 1. But then what next? So just like in the previous video, again, go watch the previous video, when you multiply this out, you get a naught times t naught squared plus b naught times t naught squared plus c naught times t naught plus d naught. But then none of the other coefficients are going to be in this equation. So they're all going to be 0, etc. And then it's going to happen again. We're going to get more t values here. I won't write them out. Okay, I'm just going to write dots to represent them. And then a bunch of zeros. So really we're going to get like a box of t values here. And then for the, so that, and that box will get multiplied by these 4 coefficients. And then below that, we're going to get another box that will get multiplied by these 4 coefficients. And then another box that will get multiplied by these 4 coefficients. And everywhere else will be zeros. So normally we have this big 20 by 20 matrix that's difficult to solve. But in this case, you can see we have a matrix that's mostly 0. And there are additional optimizations that we can do to these, because we chose our constraints very carefully. There are additional optimizations that we can do that actually make this matrix so that there are only 3 diagonals of numbers. I'm not going to go over those optimizations because they're honestly kind of boring. But then at the end of those optimizations, you just have these 3 rows of numbers right here, and that's called a tri-diagonal matrix. These pop up a lot in numerical analysis. Honestly, I can't like do a full treatment of this without, without going into a lot more depth than I'm willing to go into these videos, which is regretful. But if you're interested in this subject, go pick up a book on numerical analysis. It's fascinating. Like solving a tri-diagonal matrix is a really interesting thing. But we're going to assume that we have a tri-diagonal matrix solver that can get us all of the coefficients up here that we originally wanted. So great. So we've solved for these coefficients, and now I'm going to take the already made cake out of the oven, and we're going to go to the code section of the video and see an implementation that I've written that does exactly this, solves a tri-diagonal matrix. And we're going to see some cubic splines at work. See you in a moment. All right, I'm happy with that. Oops. What did I just do? Did I do something bad? Did I press these buttons? No. No, that's fine. All right. Starting. Okay, I have a little editing to do there, but that's fine. Ooh, already 11 minutes. That was a very long explanation. I swear, I can never get these videos below 10 minutes. Just never happens. Never happens. So linear interpolation, we're gonna move that to cubic splines. Save. Maybe I shouldn't call everything untitled, and then I wouldn't be writing over my stuff all the time. So, then the question is, which part of this video should I actually write code for? I can't write code for any of this part because I didn't go over that part. I completely skipped it. This is solving the tri-diagonal matrix. So instead, here we go. This is where I write. This is where I draw the stuff. Yeah, but we didn't really talk about drawing either. Yeah, I guess I just won't be writing any code for this section. There's just no interesting code to write. I already wrote a bunch of code on stream, so people can just come see the code I wrote on stream, honestly. Yep, I'm just going to take the cake out of the oven. So let's do it. So here we are, and on the right I have a cubic spline implementation, okay, that takes a fixed number of spline points and does a tridiagonal matrix solve. All right, and that's all this junk right here. This all solves the tridiagonal matrix, and it generates all of the coefficients for the piecewise cubic polynomials that will constitute our cubic spline. So, and then here on the right, I go through and I draw a box at each point that each control point that I've specified. And then I draw lines between them. And then I draw a few more boxes that are like surfing along the roller coaster. Okay, and we're gonna see that at work. And it's already built. There's unfortunately no interesting code to write for this video because I completely skipped over the tridiagonal matrix solver, so sorry about that. But here we are, and we can see my roller coaster going by. It has some interesting properties here that I'm going to point out. So for one, when you have your control points close together, because the cubic spline assumes, my implementation anyway, assumes that there's a constant time between each of your control points for the roller coaster. So because of that, it has to take the same amount of time to move between 2 points. If the 2 points are closer together, then the roller coaster cars just have to move slowly. So you can see they slow down a lot between here. You'll also see that all of these 7 points are in a straight line, but the cubic spline itself is not in a straight line. It has taken like some data from the next point over, which is way far that way, and you see you have this like overcompensating effect. So cubic splines do that, and you can work around that. Like you can add a few more control points in there and smooth out a little bit, but it's something to be aware of that cubic splines have this property. Sometimes it's good, and sometimes it's bad. So in the next video, we're going to look and see what we can do about the problem of this roller coaster that changes speed all of the time, depending on the distance between the oh, you know what? We can't do that quite yet. First, we have to cover arc length, which is actually a differential geometry topic, but it looks like we have to cover it. So we're going to cover arc length. And then we're going to cover, after we've covered arc length, we're going to cover how to make the roller coaster move at a constant speed, which I realize is not something you'd ever want a roller coaster to actually do. But you can use cubic splines, for example, to control camera movement. You can have your camera move along this cubic spline, and maybe your camera you want to move at constant speed. So that's what we're going to do over the next couple of videos. It's going to be great, and I'll see you then. All right. Stop recording. Where's my mouse? Ah, my mouse has disappeared. Cool. Come on. Come on. Drag this. Here. Okay. So that clocks in at like, yeah, 15, 16 minutes. Not terrible. I'm disappointed that we didn't cover tridiagonal matrices, but like it's already 15 minutes, and tridiagonal matrix would it would multiply the amount of work we'd have to do for this video by like 4 or 5, factor of 4 or 5, which means it would be an hour-long video, and that's just not feasible. So I'm gonna get to editing this video because it's so close to GDC. I'm like super busy and I actually have to bounce now. So we're only gonna do one video this week. I know we usually do 2. But I'm gonna try and get back to this next weekend. Might not be able to because I'll just be getting back from GDC and so I'll be catching up with everything. So, you know, maybe it'll happen, maybe it won't. We'll just wing it, and if not, then the weekend after I will definitely be back and we'll be doing arc length and quadratures and all that good stuff. So, great. Thank you everybody for joining me. I appreciate the comments and questions and corrections, as I am apparently in very serious need of corrections. Completely unsurprising. But thank you everybody for joining me, and we'll see you again next time.